Okay, thank you. Michele asked me to give this talk about the history of LIGO something over a year and a half ago, and I have sort of one rule, which is I never talk about history. And so he's managed to make me break down. When he first asked me, I told him no. When he asked me a second time a few months later, I told him no, never. When he asked me a few months after that, I said absolutely not. When he asked me the fourth time, I said no, 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 and by which he heard April. So that's how I ended up doing this. And if anyone wants to know how I learned never to talk about history, I can explain that later. That's quite an interesting story, but it's not for here. So I'm going to give you an idiosyncratic history of LIGO. I don't think there is such a thing as an objective history of LIGO, not for the technical things. So I'm just going to pick out a few things that I like. By the way, idiosyncratic means peculiar to the individual. So if you don't like what I picked out, well, that's just your tough luck. That's what I picked. It's the things that I felt I could talk about. So the outline, I'm going to review some of the technical history that people don't remember that much. Some of the developments that enabled LIGO from the early days, and with an emphasis from pre-1995. And I picked pre-1995 because that eliminates most of you from this history, and there are only a few people that I have to contend with who remember things differently. I'm going to talk a little bit about the invention of laser interferometers, some of the noise sources, some that are important, some that are not so important. I'll even talk a little bit about some of the way the requirements for LIGO, initial LIGO, were developed. Finally, a little bit about international collaboration, one slide on that. The goal here is to help us appreciate how little we knew when we started this, how much we've come, and how far we may still have to go in this endeavor. And finally, one of the things that people will see is you'll learn a little bit about what all those old guys that you see at meetings did when they were young and productive. I added that at the end. That wasn't one of my initial goals, but I realized that was coming out. And finally, I'll say, I would like to emphasize, this is not comprehensive. It's not designed to highlight everybody's contribution. It's not designed to be in order of importance of the contributions. It's not even guaranteed to be 100% correct. I did refer back to a lot of old papers in preparing this, so it's probably somewhat correct. As I said, it's viewed from within the context of LIGO, so it won't even have all of the full international context. In preparing this and in discussing how these different things develop, there were three reference documents that I kept coming back to that are so central to the technical history of LIGO that I think they should be introduced now. The first one is Ray Weiss's Research Laboratory for Electronics paper. This was the paper he wrote in 1973. It was published in this obscure MIT internal journal called the Quarterly Reports of the Research Laboratory of Electronics at MIT. It grew out of an undergraduate seminar that he gave where he wanted to explain to people how gravitational waves, what they were, how they could be detected. Out of that seminar, he started to think about noise sources and so on. It became a very central paper in this. And so how we understand the operation of these detectors, many of the concepts go back to that RLE paper. The second thing I'd like to point out is something called the Blue Book. This was a study done primarily by the people at MIT, Paul Lindsay, Peter Salson, Ray Weiss led it, but it was also involved a couple of engineering companies, Stone Webster and A.D. Little. It was dated in 1983. It's really hard to find if you don't know where to look because it was never really published. On the other hand, it was a very comprehensive document. The final document that I will refer to fairly frequently is the construction proposal, the 1989 construction proposal for LIGO. The proposal team, Robbie Vogt, Ron Drever, Ray Weiss, Kip Thorne, and Fred Robb, but it included contributions from a large number of people and was central to LIGO. The RLE paper, I'll just mention, so you can see it looks just kind of like an interferometer. You've got test masses, you've got a beam splitter, you have control systems to feed back. Looks just exactly like it. It was not the first suggestion of a laser interferometer for detecting gravitational waves, but it was the first detailed noise and sensitivity analysis, I believe. It included things like shot noise, radiation pressure noise, thermal noise, seismic noise, gravity gradient noise. Almost every noise source that we worry about now can hark back to something in that RLE paper. The Blue Book was a science and engineering study of feasibility. It was a comprehensive in scope. The chapter titles, if you just go down them, sources of gravitational radiation, physics and detection, prototypes and optical concepts, noise sources, vacuum system, site survey, construction details, even a proposed design. It was important because things inside of that document are starting to look like present-day LIGO. The basic shape for the tube covers goes back in some ways to this. And it was also important because it was the first engagement of engineering firms. And then the '89 proposal, it was in 2 volumes. Many of you have probably seen it. It had the famous picture of a LIGO next to the mountains. It had 2 volumes. The first one was the science case, detector physics, noise sources, prototype experience, all of the science. The second volume was the engineering design and the cost basis. And in many ways, I actually think that second volume, the engineering design and the cost basis, for something that had never been built, was remarkable in its accuracy and its comprehensiveness. It defined the sensitivity goals, the phased approach, the scope of LIGO. It even had the noise thing, which eventually became the SRD, the science requirements document for LIGO, and the target specification for the noise curves. And amazing that we were actually able to reach that goal. So, who invented the laser interferometer gravitational wave detector? Everyone asks that. And it's not even clear. I'm not sure I can tell you. It looks to me as if there were multiple independent inventions of the idea. Ray Weiss in the RLE paper cites that there were many people, he actually says that had been suggested many times. He cites one article by Pirani in the Acta Physica Polonica, a Polish journal of science. This is actually not, he says it's the use of interferometry to detect gravitational waves. It obviously wasn't laser interferometers, because in fact the laser wasn't invented until 4 years after this article was published in 1960. How Ray found that article and cited it in his RLE paper, I don't know. I've never seen the article. I just know that Ray pointed it out as one of the early suggestions. Thing that's oftentimes cited as the first suggestion is an article that was done by 2 theorists, Gerstenstein and Pustovoit, in the Soviet journal JETP. It was originally in Russian and then translated into English. It's not cited in the RLE paper, so I don't suspect that Ray knew about it when he wrote this. That actually isn't 1063, that should be 1963. Sorry. And it's people often say that that was a paper that was not widely known in the West. On the other hand, I do know, for example, I discovered as I was poking around, that it was noted by Brzezinski, who wrote a paper called Gravitational Radiation and the Prospects of Its Experimental Discovery, also translated into English in 1966. So how it is that this other paper wasn't noted by people escapes me a little bit. Of course, there was Ray's RLE paper, which represented, I think, an independent invention of the concept. And he says that his idea for this goes back several years, unquote, there, before this paper, which was written in 1972, published in 1973. And that RLE paper also cites Philip Chapman as having independently proposed the technique. Philip Chapman was with NASA Houston. It turns out I looked up Philip Chapman. He was the first Australian-born astronaut. And in fact, the first Australian-born astronaut who never actually went into space. But he had been at MIT, and I presume had been somehow seeded by discussions with Ray to do this. But he apparently also independently invented the laser interferometer. At the same time, these ideas were being generated at MIT by Ray Weiss. There was also work going on the first interferometer prototype at Hughes Research Labs. They actually started apparently in 1966 doing gravitational wave research, and in fact they published in 1971, a couple of years before Ray published his article, they published a description in Applied Optics. And in that, the authors, primarily Forward, Robert Forward was I think the lead of that. He cites that the idea of detecting gravitational radiation by using a laser to measure the differential motion of two isolated masses has been suggested often in the past. And he cites a telephone conversation that he had with Joe Weber as the first time that was suggested to him. By the way, that paper also in 1971 acknowledges discussions with Ray Weiss and with Philip Chapman both. So there was an active discussion going on. And the first searches with this Hughes research, the forward interferometer, was actually published in 1978 in PhysRevD. It's kind of interesting to go back and look at those old papers. For example, you see how they described in that first 1971 article, the forward thing. We always talk about how the gravitational wave comes down on an interferometer, shrinks one arm and stretches the other. They didn't describe it that way. It comes in along one arm, which is the reference arm that stays stable, and it shrinks and stretches the perpendicular arm. So that's how they, in fact, described it. They had actually recognized the beam pattern of an interferometer, but that's not how they describe it in their introduction to the paper. It was not a suspended mass interferometer in the traditional sense. They didn't use a pendulum suspension. They put it on springs at a nice 3 Hertz isolation suspension. The data analysis section is quite interesting. It's called calibration of the ear, because they actually listened to the tapes that they'd made of the interferometer output to try to pick out the pops that would be the gravitational waves coming in. Data analysis is kind of pretty much not progressed much beyond that. Okay, so let's move on to the next thing, residual gas noise. This is not the most interesting noise source to the typical physicist, but it's a nice little exercise in how you've learned things, how you forget them, how you remember them. And it has some importance because, in fact, the vacuum system is one of the largest cost drivers in LIGO. Okay, so the residual gas noise was not actually even mentioned in Ray's RLE paper. It's one of the few modern noise sources that doesn't go back to the Ray's RLE paper. However, the Blue Book, done in 1983, has essentially a correct treatment of the noise due to the residual gas. It's the statistical fluctuations of the number of gas molecules in the beam. And this basically is, you count up the number of gas molecules, square root of n, and those are the fluctuations, causing a change in the index of refraction. They have, in fact, in that Blue Book, set the initial LIGO requirement at 10 to the minus 6. It wasn't called LIGO then, but for an interferometer of initial LIGO sensitivity, they set the requirement for the vacuum at 10 to the minus 6, which is, in fact, what we set for initial LIGO. I shall say that there was an independent formulation of the gas noise done by the Garching group, the group in Max Planck, Garching, or Munich, sort of bouncing back and forth between those two Max Planck things. And written up in this paper, you might recognize one of the authors of that paper, the lead author. They referenced an unpublished derivation to Albrecht-Rüdiger for that gas noise. It was essentially the same as in the Blue Book. So you might say, well, okay, another independent invention, everybody knows what gas noise is. It was not an entirely linear progression. There was a 1987 LIGO R&D proposal, which was to get ready for a big construction proposal. That initial LIGO requirement got quoted there as 10 to the minus 3 torr. Believe it or not, Kip's looking very pained, but it was there. In the 1989 paper, there was a new formulation of the problem in terms of forward scattering amplitudes, the forward scattering matrix for gas molecules, a wonderfully detailed thing. It looks really high-tech and physicky. Unfortunately, there was a simple algebraic error that was made there that ended up with the wrong formula. It gave approximately the correct vacuum requirement. That's probably why nobody really noticed that the formula was incorrect until several years later. And it was finally resolved with an experiment that Mike Zucker led, where they measured the optical path length fluctuations in the 40-meter interferometer, looking at the change in the noise level, the noise floor, as a function of the pressure of the gas for several different gases. And in fact, that really nailed this noise source to the factor of 2 level. Thermal noise. Thermal noise was actually one of the most important and complex fundamental noise sources. And I probably won't do this one justice, but I will talk a little bit about some of the early history. Thermal noise was recognized in Ray's RLE paper very early on. It was in fact the third noise source listed in that paper after shot noise and laser frequency noise. That's, I think, the measure of the importance that Ray gave it. What he had in that paper was a single mode analysis for thermal noise, assuming viscous damping. He did mention that you have to worry about both suspension modes and internal modes in that analysis. It's interesting, however, to look at that RLE paper and realize that although all of this stuff is there, suspension modes, internal modes, the suspension is not defined as a pendulum. And in fact, it's described as a long period seismometer suspension. And just to reinforce that, if you look up here, you see that the suspensions are described as horizontal seismometers. Okay, it wasn't obvious at that time that he thought a pendulum was the ideal thing. In fact, he says the suspensions are critical components in the antenna, and there is no obvious optimal design. I think that was later. I mean, it became fairly clear. So that even by the time of sort of, you know, the early 80s, everybody was using a pendulum suspension because it's of simplicity. However, Ray did point out that, you know, if you did this, you'd need a good high Q in your suspension mode, and he quoted a value of 10 to the 4 for the suspension mode of that horizontal seismometer. He did recognize the multi-mode nature, however, and again, a quote from that paper: the general problem with suspensions in the real world is that they do not have one degree of freedom, but many. He recognized that there were multi-mode issues in the thermal noise. The Blue Book, in 1983, you fast forward 10 years, it basically is still the same single mode analysis of the thermal noise for doing the noise estimates in the Blue Book. However, people were beginning to recognize the complexity there. There's, again, a statement: a frequency-independent stochastic force is at this time still only a conjecture. That meant that they were actually starting to think about things other than just viscous damping. He also said there are situations where a blithe application of the model will give the wrong results, and they cited coupled oscillators and servo damping as both cases where the simplest single mode analysis gives you the wrong answer for the thermal noise. One of the problems with this thermal noise, and as I tried to unravel some of this early history, is that things are largely unreferenced. So the source of incorrect information is really hard to pin down the conclusions. So, for example, in that blue book, the material Q for fused silica is quoted as 10 to the 4th. Okay. Now we now know that it's 10 to the 7, 10 to the 8 are quite plausible kinds of numbers for that. Where this number came from, no idea. And I'll just show you the noise budget from the blue book, where you can see here's the thermal noise from internal modes, here's the thermal noise from the suspension modes. I should point out, I claimed that they had the correct formula for gas noise, and if you look at the two gas noise curves, 3 and 2 here, you'll see that they have the incorrect slope. They should be flat. I don't know what happened there. The formula in the blue book is correct. It's this plot which seems to be wrong. Okay, so not everything is perfect in the old days. The 1989 proposal, as far as I can tell, that's the first time in the literature that the fluctuation dissipation theory was mentioned. I couldn't find any other previous mention of it. However, it's mentioned as the source of the thermal noise, but it's not really used. And in fact, the noise estimates are still based on the viscous damping, the single mode models that had dated back to the Ray's RLE paper. They did now start to talk about frequency-dependent losses. The damping can be frequency-dependent, so that a simple measurement of the Q of a resonance is not sufficient to predict the thermal noise off resonance. They mention it, they don't do anything with it. They recognize the importance of overlap between the mechanical modes and the optical modes, something that hadn't been recognized prior to this. They point out estimates of the equivalent gravitational wave strain depend upon the overlap integral of the optical mode shape with the mechanical mode of the mass. So the understanding is growing steadily in this by the time of the 89 proposal. The final thing I'm going to talk about in terms of thermal noise is Peter Salson's paper. I think most of you are familiar with this. It's called Thermal Noise in Mechanical Experiments, published in PhysRev in 1990. And one of the things that I think makes that paper so important as I come back and read through the history of this is that it has a complete set of references. You can go there and you can actually understand where did that formula come from, where did these values for the numbers come from. It's the first time that I've seen a complete set of references in the area of thermal noise. Thermal noise tended to be something that was completely under-referenced. For example, that Shoemaker paper that I mentioned about the Garching interferometer, its thermal noise reference discussion had a single reference, but only to how you calculate the mode resonant frequencies of a cylinder. Nothing about how you actually translate that into a thermal noise. And I think that's one of the things that I take away from this, having gone back and looked at this, is that by including these references, this paper made a tremendous leap forward, and that much we could have made a lot better progress if people had been citing proper references early on. This paper was begun while Peter was at MIT, Peter Salson was at MIT, during the writing of the 89 proposal. So it was obviously influenced by the things that were coming up and showing up in the 89 proposal. It was completed during a sabbatical that he took at Gila, I believe. And it's remarkable for the fact that it has, among the first presentations, as far as I would have said the first presentations, but I'm not absolutely sure that they are the first presentations in the gravitational wave literature, of structural damping on an equal basis with viscous damping. First time that I've seen people talking about thermoelastic damping. It's the first clear discussion of how the fluctuation dissipation theorem can play into these things. It's got a discussion of multi-mode systems, systems with localized losses, and so on. And in fact, this paper, to my mind, sets the stage for a lot of progress in subsequent years. Your 11's work, the modern appreciation of coding thermal noise, and a number of other things. I think all that harks back to that paper. Really a very significant paper. I think most people recognize it as being very important, but I just wanted to emphasize that. The mirror figure requirements for initial LIGO. It turns out that was one of the biggest challenges in initial LIGO. And the initial LIGO requirement, well, just point out to you from the beginning, was 0.6 nanometers RMS over the central portion of the optics in initial LIGO. So that's really a very demanding requirement. So where did that come from? Well, first of all, there's no mention of the requirements for mirror figures in the RLE paper. It's not mentioned in the blue book. The first time I found anything about mirror figure requirements was actually in this 87 R&D proposal that was submitted, where they say that the mirror specifications, including the figure and slope errors, have been developed with industry. They don't actually give much more detail than that. That's basically the statement. There's really no clear discussion of where it comes from. The requirement is given as 20 nanometers. And what you have to remember is, at that time, the laser wavelength was 500 nanometers, half of what was used in initial LIGO. So if you correct for that difference in wavelength, you actually find that this specification is about 60 times poorer than what we needed for the initial LIGO requirement. In the 89 proposal, that same requirement is repeated without any further elaboration. It's still for a wavelength of 500 nanometers. And if you see down here, they talk about, in that proposal, the figure error, 200 angstroms, 20 nanometers. So it's still that factor of 60 off from what's required. I've been quoted many times, well, I know I've said it several times. I think if people had really known what the mirror requirement was when that 89 proposal was written and had put it into there, I think that there's a good chance that proposal would not have flown, because I don't think people believed that those kinds of mirrors could be made. So how did that get resolved? What was happening? Well, people started to worry about, not about the mirror figure requirement. The initial concern was about the substrate uniformity and how the configuration that we were using for the interferometers, with the beams being transmitted through the input test masses, how that affected the contrast at the beam splitter and therefore the recycling gain. And so people started to look at that. Mike Burka of MIT in particular was one of the first people to do that. And he initiated a program of measurements and modeling to try to understand the effect of substrate inhomogeneities on the dark port contrast. So he started making measurements of how uniform the phase fronts were going through those. He started making models, a modal model and then FFT models, to try to understand how the substrate homogeneity affected this. People began to then say, oh, wait a minute, maybe we ought to look at how the surface figure looks. And so by 1995, people had recognized that there was a requirement on the surface figure of the optics. And so by 1995, the requirement on the LIGO optics had tightened to lambda by 400. Now, that was still about the time, that was just about the time that we were changing from 500 nanometer argon ion lasers to 1064 solid state lasers. About that same time, we discovered the AXAF test flat. And that was an article which was pivotal in this. It was a test optic that had been polished by Perkin-Elmer for a NASA X-ray satellite called AXAF. So it wasn't actually an optic that was going to be used except to test the X-ray optics for this satellite. That test flat, however, was very, very good. It had approximately 1 nanometer RMS surface figure, about a factor of 2 from what the eventual requirement was. And it was that discovery that actually led us to realize that we could, in fact, meet the requirements of this. And then, from that, the requirements still evolved a little bit more, improved modeling, so the specifications improved about another factor of 2 from what had been tightened up another factor of 2, so we got down to the surface uniformity, 0.06 nanometers. The uniformity for the coatings, this was something that was recognized later on, that we would also need uniform coatings at the 10 to the minus 3 level in terms of their thickness. The final challenge was to convince industry not only that they could do this, but that they were already doing it. In fact, there were companies that were already making optics that were meeting LIGO requirements, and the companies didn't know it by factors of 50 to 100. Okay, final noise source I'm going to talk about is mirror orientation noise. Again, it's not a particularly dominant noise source today, but it was a dominant noise source in the 40-meter interferometer circa 1990. And it's significant in my mind because it's one of the first places where bilinear noise mechanisms were studied. I'm not sure if it's the first one, but it's certainly one of the earliest ones. Okay, so mirror orientation noise, the angular fluctuations, how they couple to an interferometer's output. Again, that's not mentioned in the RLE paper. However, the Blue Book has it, it's mentioned, but it's not really discussed as a serious noise source. In fact, they say these effects are only second order in the angles. And they give a formula here that shows that the apparent change in the cavity length is second order in the angle of the mirrors. And so they were able then to say, well, if it's second order, that just means it's not that important. So you go back and you figure out what this is, you take the square root, and that gives you the requirement. It's not discussed in much more detail in the 89 proposal, but the requirements that they put in here still indicate that it's viewed as something that's second order. In fact, when you look here, these angular fluctuations, here they talk about beam stability, but it's clear from the discussion that they're applying the same requirement to the angular fluctuations of the mirrors, 10 to the minus 12 radians per root hertz, a position stability of 0.7 nanometers or millimeters, and if you actually put those into the correct noise formula, you'll actually find that we would be missing the initial LIGO goal by about 4 or 5 orders of magnitude. How did this come about? Well, at this point, this was a limiting noise source, it turns out, in the 40-meter. The 40-meter interferometer noise was high, and it was not understood about this time. So remember, this is 1990-ish, and the 89 proposal was submitted in December of 89. So it was actually rather important that the prototypes have some improvement, have good sensitivity, because the LIGO construction proposal was being reviewed, and the funding for LIGO construction was contingent upon having, showing that we were making progress on the sensitivity of the interferometers. The person who actually was in the lab doing this was CaJAGWR, and he began investigating things. He was looking at all of the 40-meter systems, trying to understand what this unknown noise was, and he began investigations of the orientation control systems. I think his interest there was piqued originally by the fact that the spectrum had lines at the multiples of 60 hertz. That's not surprising. What was a little bit surprising was that those lines were actually broad. They had some width to them. And they showed an obvious sideband structure. And so he began to poke at what did that really mean. One of the early experiments he did was to inject a signal. this happened to be at 250 hertz, into one of the angular control systems of one of the test masses in the 40 meter. So he made a nice big peak, and then he saw, lo and behold, that he picked up these broad wings with this sideband structure on top of it. And so he began to suspect that that was the source of this. He did some calculations. You know, here's his little sketch. That's his handwriting, showing how you know, the angles of two mirrors, you know, a flat mirror, a curved mirror, define the position of the resonating mode. So he worked out that geometrical length. That looks kind of not very significant in retrospect, but it was actually quite useful. His first interpretation was in terms of a static misalignment, namely that this spot on the mirror was offset by a static amount by a static misalignment, and that then changes in the angle of this mirror would couple to length by that offset. Okay, and so that was his first interpretation. That evolved, so he did a set of measurements where he actually displaced the mirror, changed the alignment of the interferometer, moving the mirror, the spot on the mirror by, you know, approximately millimeter steps, and he found in fact that there was a nice correlation with the noise level in the signals that he was generating. But that evolved over discussions with other people. Mike Zucker, in fact, I think was one of the key people that he was discussing that with, where it was actually, you find that the peak height, yes, it does have that linear dependence, but there's a minimum here. And this is the RMS motion. When the beam spot is on average well-centered, it's got an RMS motion. And it's the low-frequency RMS motion that's mixing with the high-frequency motion to produce sums and differences. It's a nonlinear mechanism, or what I would call a bilinear mechanism. And the point is that this was a critical thing. It improved the noise in the 40 meter by orders of magnitude. This is what it was before the fix to the control systems. This is what it was afterwards. And it was, in fact, this change, I think, was critical to the funding of the LIGO construction proposal. And you could then see that the noise, he could predict what the noise was for the various control signals contributing to this. It hadn't been completely eliminated, but had largely been eliminated. Published by Seiji and Mike Zucker. This sort of thing looks obvious now in retrospect, but I think it's underappreciated in my view. And I think it opened many people's eyes to the large number of bilinear noise sources that exist in these interferometers. Final thing I'm going to talk about is international collaboration. And again, here, this has been an incredibly important development over the last 5 years. So you might ask, well, what in the world do I have to say about that in the 1990, you know, pre-1995 era? And I just stumbled across this and looked at it and saw, here is a description of the LIGO Virgo gravitational wave detection system, okay? And so sometimes dreaming pays off big. That was in 1992 that Kip had the audacity to write that there would be a LIGO Virgo gravitational wave detection system. I do, actually. I remember you coming to me with this paper, and I encouraged you to go ahead and do it. Even though at this time, you know, those two collaborations were entirely separate. Anyway, so conclusions. I don't know how you actually have any conclusions for a historical talk. A lot of stuff happened in the past. A lot of stuff's going to happen in the future, and we've talked about some of it. I think some of the things that were done in the past were right, and that the insights that people had were amazing. So if you go back and look at some of those papers, you'd say, gee, these were really far-sighted things. On the other hand, some things were not right, and when you look at it, you say, how in the world could they have missed this sort of thing? So that's just how it is. And my final thing, let's not waste time with questions when there's wine in the next room. But I will take questions if anyone has.
Stan, I was struck with your comment about how little you guys knew when you made the board proposal. It seems to me that's an era that's passed. I don't think anything that the NSF would fund in this environment passed muster without the most rigorous understanding of predictions. Wonder how much science does it get?
Well, I think you're right. There's, I guess for people in Evo land, that was Albert saying that he didn't believe that in the current funding environment at NSF, that projects would get funded where everything wasn't known. And I think the answer is, we thought we knew, when that proposal was written, and I say we in the sort of the royal sense, since I wasn't actually on that proposal, I wasn't part of the writing of it, but I feel some significant kinship and ownership with the people that did this, ownership in a positive way. They legitimately thought they knew what the requirements were, and they stated them positively. And it was only later that the recognition came slowly that maybe there were tighter requirements that hadn't been found. I suspect that still happens with big proposals. People find that, they think they know how to do something and it doesn't quite work out, and so, they do heroic things to make it work. So yeah. We might lose something from the fact that we need to prove that we really know how to do it. I think we also can find that we can do things much better. The modern tools, just the fact that you can typeset stuff on computers and adequately reference them without having to sit at a typewriter and use correcting tape to correct out things and change references and so on, is a huge advantage of being able to search through documents and find information in a positive way. Is a huge advantage now. I mean, that's one of the things that I find that I was struck by in this, is how hindered I was in actually digging through the information because stuff wasn't adequately referenced, because it was really a pain in the butt to do an adequately referenced document. The thermal noise was the clear example of this, where Peter Salson had done this one article that was beautifully referenced, and everything prior to that, as far as I could tell, was just hearsay and verbal folklore. So there are advantages we have now. Alan.
You mentioned mirror reflectivities.
No, I didn't.
Want to say anything about that?
Oh, Alan noted that I didn't say anything about mirror reflectivity and mirror losses. And there the answer really is, what LIGO's role in the development of low loss mirror coatings was mostly to stand on the sidelines and watch other people do it. There was I would consider one significant contribution that was made to that effort from within LIGO, and that was the diagnostic technique of using cavity ring down to actually measure the losses in very low loss coatings. That was a significant contribution to the people making those coatings, but we really had nothing to do with the development of low loss coatings. That was all driven by industry, I think.
You mentioned that there was a 78 PRD paper that was the first experimental attempt to measure gravitational waves. What did they, the sensitivity must have been very terrible. I mean, what did they, just out of curiosity, what did they think they would find? Did they actually think they had a chance of finding stuff?
Well, okay, so for the people in Evo land, that was a question about Robert Forward's 78 paper. I don't actually know when that research was done. I suspect several years before 1978.
Measurements were made in the early 70s.
Yeah, so Kip confirms that the measurements were made in the early 70s, and it just took a long time to write the paper. That was, by the way, not the first attempt, obviously, at measuring gravitational waves. People were doing that with bar detectors, attempting that long, even before that first interferometer was built. But the idea was that maybe by building a broadband detector, there would be the ability to add, find stronger signals that were not necessarily resonant with other things, with the bars, that might provide additional information. As I recall, the sensitivity of that interferometer was not quite as good as the bar sensitivities, but it was not far off, within a factor of 10. Do you remember, Kip?
At least within a factor of 100, maybe a factor of 10.
I think it was about a factor of 10 poorer than the best bars that were operating contemporaneously with it. But it was broadband, and that was the advantage that it brought to the table. Anything else? Okay, well, thank you very much.